Hey guys, welcome to Budding Genius Academy. If this is your first time, welcome, and if you're returning, I hope you find something in these videos that maybe you didn't know before or that you didn't learn in the past videos. My name is Amelia. I am a second year student at the University of Toronto. I'm double majoring in mathematics and statistics, and I've been tutoring for about 4 years. So I have a lot of experience teaching people and I love doing it. So I'm really excited to teach you guys something today about derivatives that maybe you haven't seen before or you're revisiting because you're still interested in it and you just want to, refresh your memory. So as always, if you like what was in these videos, you can book online at bg-academy.com, and we're offering summer classes. We also have one-on-one tutoring. We have all sorts of stuff for anybody who's interested in learning a little bit more about math or who's maybe a little bit worried about going into the school year next year and wants a bit of a refresher. And also, at the end of this video, there will be a quiz. And if you get all the questions right on that quiz, you can send us an email at the email address at the end of the video for 20% off of any summer classes that you book or any tutoring sessions. So stick around through to the quiz and get that 20% off for sure. And book a summer class in tutoring, and we would love to have you. But for right now, let's hop into it. All right. So here we are. We're hopping into a lesson about derivatives. So first we want to talk about the practicality of derivatives. So let's consider a function y equals f of x. And let's call this line that we've written here that function. So it doesn't matter what this function is. This can be anything. We'll just have a line right here and just a basic standard name, f of x. So if I were to ask you at any point, so say for example at this point that we've chosen right here, A, we want to find the tangent line. We want to find the line that intersects through this point A at only one spot. And it touches right at A, and then it moves on without touching anywhere else. That's what a tangent line is. Maybe be better illustrated down here where the curve is a little bit steeper, but it just sort of touches once and then continues on like that. And that would be the tangent line right at this point right here. But we can map out this tangent line, and then we can say, because it's a line, we can take the rise over run, right? So, the rise over the run and try to figure it out that way. But that's not going to give us a super exact answer for the exact equation of the tangent line right at that point. And there's a lot of reasons to want the tangent line. It helps with finding the rate of change at this exact moment for anybody who's interested in physics. That comes up a lot. But just trust me when I say finding the equation of a tangent line at any given point of a function is a very useful thing to do. So being able to draw this tangent line is helpful, but it's not super helpful, right? Because what if I draw it again and I draw it like this? That could theoretically be only intersecting at one point, but it's a different slope. And this theoretically intersects at only one point because we don't have the rest of the function to say that it doesn't only intersect at one point. So finding this equation of the tangent line is going to be a little bit trickier than just being able to draw a line that looks like it's sort of tangential to the function. So let's consider the slope of this line when we're trying to find the tangent line from f of a, so this point right here, to f of a plus h, which is this point right here. So we're going to consider the difference between these 2 points right here to be a plus h minus a is just h. So this is h, the difference between these 2 points. So if we draw a line and we start it at f of a, so kind of right here, I'll draw it in blue, and we draw it all the way down, oh, this is not a very good line, to this point right here. This line isn't tangential, is it? Because it intersects at 2 points, at f of a and f of a plus h. But it starts to approximate sort of the slope of that tangent line that we're looking for. What if now we decided to make h smaller. Let's call it right here. And so now this is an a plus h. This is a plus h. Here, let's erase this so you can see better. So now we're deciding to say that this is a plus h. So this line here is h. So this h is getting smaller. Now we can recalculate the line between this same starting point and this point here, and the slope of it is a little bit steeper, and it's starting to look like what we could maybe guess. If we were to guess this tangent line, we would maybe guess that it looks sort of like this. So it's starting to look closer and closer to what that actual tangent line is. And again, we could make this h even closer. Let's choose a new color. Let's make it, I don't know, purple. So call this h here. And then when we draw this line, this looks even closer to a tangent line. So as that h gets smaller and smaller and smaller, it starts to look more and more like the actual tangent line of just this one point right here, which again, we still don't know how to find the equation for. But what we can do is approximate it by finding this equation between a right here and a plus h right here, given h that we choose. It could be any h. So if this a is 1 and this is like 11, h is 10, right? But then we could say, oh, well, we want to move it to 5, so h is 4. And then we wanted to move it to 2, so h is 1. So h can be anything that we choose. So how would we find the equation of this line? Presuming that we want to approximate this and we say, it's close enough to what we think the equation of the tangent line is, given just the a and the h. Well, it's a linear equation, right? So we can consider this to just be the rise over the run, right? So if this is the rise and this is the run, we're going to do it with the two points that I've circled. So this a plus h that we had originally. Well, the rise is the difference between this point here and this point here. And so we know that this point is f of a plus h, right? Because it's just the equation at this given x, which is equal to just this random number, a plus h. And this point right here is known as f of a, because it's the function at this given point a. So the rise is the difference between these two, right? Let's call the slope of this line m, and this equals the rise over run, right? So this is equal to f of a minus f of a plus h, right? It's that first point minus that second point. And then this is over the run, right? So the run is this first one minus the second one, right? So we can say a minus a plus h. And we can rearrange this so that it makes it a little bit more simple. So we have f of a minus f of a plus h over a minus a plus h. We distribute that negative sign in, right? So it becomes a minus h, which we can then simplify, obviously, because a minus a is just 0. So it becomes negative h, and I don't love having that negative sign in the bottom, so we can just rearrange the top and the bottom, right? So we then just get f of a plus h minus f of a, right? We just factored out a negative sign. Factor out a negative sign in the bottom. There. So now we have an equation for this line between a and a plus h. So, what if h is as close as possible to 0? Well, we saw up here, when we moved h in closer to a over here, this way, then the equation of the line started approximating closer and closer what we think the equation of the tangent line at a would be. So let's do an example of just calculating what happens if this h is as close as possible to 0 using this new equation that we have right here. Here, I'll write it out again down here so you guys can see it. It's f of a plus h minus f of a over, it's a plus h minus a, or just a minus a plus h, or just h, and it's just the rise over run. Sorry, that was a bad h. And it's just the rise over run of the 2 points between a and a plus h. Now we can't have h actually equal 0, right? Because then this equation right here that I just wrote out would be over 0, and anything divided by 0 doesn't exist. So h can't actually equal 0, but we can get h as close as possible to 0, and that will help us out, I think. So let's consider just a random example where I said a equals 3 and f of x is equal to just x squared plus 2. Just a random function, right? So let's consider that first one. So when h equals 0.01, then we have, following this, we can just plug in what we have, right? So f of a plus h will become f of 3 plus 0.01, which is, we can just plug that in as the x, right? So it's 3 plus 0.01 squared, right? That's the x, plus 2. And that's f of a plus h minus the same thing again, but without that 0.01, right? Just the a is 3, so a squared plus 2 over 0.01, which equals, let's do some simple addition. So 3.01 squared plus 2 minus 3 squared plus 2 divided by 0.01, and if you guys have a calculator handy, you can just type it in, but it just equals 6.01. Okay, so we have an answer. It's close-ish to 6, but we can't say for certain that that would be the equation, so let's keep going. Let's do the exact same thing, but now let's make h a little bit smaller, so it's even closer to 0, right? So we can do the same thing, and we know that it ends up to be roughly the same thing, so we have, 3 plus 0.001 now, so it's 3.001 squared, plus 2, minus 3 squared plus 2, over 0.001, right? The only thing that's changing right now is the h. So the f of a here is still the same, where a is just 3. So f of 3 just equals 3 squared plus 2, right? Because f of x is just x squared plus 2. So f of 3 is 3 squared plus 2. So f of 3 plus h is just 3 plus h squared plus 2. So this 3 plus h, where h is 0.001, is just 3 plus 0.001. And now we have a new function, and we can just calculate that out as well. So if you have a calculator handy, feel free to just plug that one in. But if you don't have one handy, I can just tell you the answer is 6.001. Alright, okay, so we're getting even closer to 6 now. So now let's do h is 0.0001. So change that h to one more decimal point closer to 0. But other than that, it's still the exact same expression. The f of x isn't changing, the a isn't changing, so it's still 3 because it's 3 plus h, so 3.0001 squared plus 2 minus 3 squared plus 2 over 0.0001. And now you plug that into a calculator and you get 6.0001. So we had 6.101 and then 6.001 and now 6.001. So they're getting closer and closer to 6, right? Well, we can't say for certain that that's maybe what they're getting closer and closer to. It could be 6.00004 or something. So let's look at the other side, all right? So we can consider this now where h is in the negatives. It's getting close as possible to 0, but from the negative side. And so we could consider this here using, this is kind of a mess, this chart that we have up here, but when we had this chart up here, let's just draw a rough approximation of it. It looks like this. Let's call this point right here A. We could consider where h is negative, so this point here is a plus h. And h is actually negative 0.1, or negative number. And so the difference between, the line between these 2 points versus the line between these 2 points and all that, it still is approximating that tangent line of A, it's just coming from the other side. So we can look at that now and say, well, when h is a negative number, so we're approaching that tangent line from the left-hand side as opposed to the right-hand side, we can say, all right, the f of x is still the same, the a is still the same, a is still 3, so we have, 3, right? Follow along here, f of a plus h, so 3 plus h, which is 3 plus negative 0.01, or 3 minus 0.01. And then right here we can see it's squared plus 2 is the equation that we're using, minus that still same f of a, 3 squared plus 2, right? Over negative 0.01. So this equals 3 minus 0.01 is not 3, 2.99 squared plus 2 minus 3 squared plus 2 over negative 0.01, which equals 5.99. Okay, so we're on the other side of 6, but still pretty close to 6, right? Let's see if that pattern holds. Now we're going to do it again, but for one decimal point of h closer to 0, but still in the negatives. So we can write it out as it was 3 minus 0.001 now, so 2.999, right, squared plus 2, minus 3 squared plus 2 over negative 0.001, which equals, if you have a calculator, feel free to input it, but it equals 5.999. Okay. Again, even closer to 6. And then the last one we have for this example is negative 0.0001. So that is 3 minus 0.0001, or 2.9999 squared plus 2 minus 3 squared plus 2 over negative 0.0001, which equals, you can check on your calculator, but it's 5.9999. Okay, so when we set A to be 3, and we made the h's coming from either side closer and closer, the a plus h's got closer and closer to a, so the h's got closer and closer to 0. Then the answers that we were getting were closer and closer to the either side of 6. So when h was negative, right, so this would be a plus h is getting closer. So this h right here is negative. It's a negative number, so negative 0.01 and even closer. Then we were getting numbers that were getting closer and closer to, let's call this point right here 6. And on this side, when h was positive, and this was a plus h being larger than a, then we were getting numbers that were closer and closer but slightly larger than 6. So when we have these two forces coming together, we can make the assumption that they will meet right here at 6. So the instantaneous tangent line between f of a and f of a, the rise over run between f of a and f of a, which we can't just calculate because to calculate a linear equation you need 2 points, we can assume that it would have equaled 6. And this is where we get into the ideas of a derivative. So the derivative at a being 6, or the instantaneous velocity or the tangent line to the function at a is equal to 6, or the slope of the tangent line at a equaling 6. So I have another example for you guys here. You guys can sort of bust through this one on your own if you want another way to double check. But this is sort of just one that you can do if you want more convincing, but I think that you'll find that these numbers are just getting closer and closer to 6, and it looks like they're starting to meet right at 6 when h equals 0. You can do this example too if you want some further convincing, but that's the idea that we're trying to learn from using these really, really small h's. So this is the idea of a limit. So as h is approaching 0, right? I have a much nicer drawing than I did on the last page. As this h is approaching 0, so the distance between these points right here gets closer and closer to 0, right? Because these are our h's. Then f of a plus h is approaching to f of a, right? This point is getting closer and closer to this f of a right here because they're closing in on f of a. So if we were to draw a line between these points, these points here, and then if we made them even closer to f of a, then they'd be through here, and then if you made them right next to f of a, like just sandwiched against it, it would virtually be the tangent line. So because these f at a plus h's are getting closer and closer to f of a when h approaches 0, we can assume that if we were to imagine a world where we could calculate it directly at f of a, that would be the slope of the tangent line. So we call this the limit. So when you have, these ugly lines are hard to see. When you have a function that's approaching from this side and a function that's approaching from this side, and they're closing in on a number, call this number 4 or whatever it is, and these numbers are getting closer and closer to 4 here, and these numbers are getting closer and closer to 4 here, and we have to sort of guess what we think that this number would be, we can call that a limit. So the limit as h approaches 0 of f at a plus h equals f of a. And the way that we draw that is the limit like this. It's like it's lim. I like to write it in cursive because most math textbooks do, as h approaches 0, or as whatever number approaches whatever, of f at a plus h will equal, because we can make that assumption based off of all this evidence, f at a. So now that we have this sort of definition of a limit, we can apply this to that slope of the tangent equation that we found earlier, right? This one up here. So as this h approaches 0, and let's make this h, a plus h, and then we make the h smaller, so a plus h, and we make the a smaller, h smaller and smaller, so it was this one, and now it's this one, and now it's this one. The slope of the line between f at a plus h, so the one that was originally like this, and now it's like, at the newer point it's like this, and then at the newer point it's like this. It starts to look more and more like the tangent line, right? So, and we can actually say that as the limit of h approaches 0, as this h gets smaller and smaller and smaller towards a, then the slope of these lines between f at a plus h, so f at a plus h, and at f at a, that slope of that line becomes the slope of the tangent line. So this is the expression that we can say using a limit, that the slope of the tangent line, or the derivative of a, is equal to, as the limit of h approaches 0, is equal to this equation right here, which is the rise over run of f at a plus h minus f at a. And that might be a little bit confusing, so if that's confusing to you guys, if you guys aren't quite understanding what that means, then come back for the next video and we'll go over some examples of what exactly that means and how that applies directly to derivatives and all of that stuff. But basically what we've accomplished here is we said that we have an equation to determine the derivative of an expression f of x at a given point, a. So we can find that slope of that tangent line using this expression that we have right here. Alright, hopefully I haven't lost you guys. So I have a bit of a quiz for you here. This is like the example questions that we did before. So find this rise over run for a equals 2 of this expression here, and then map out, given that a equals 2, so a equals right here. Try to, if you can, maybe print this page or something, map out the h's getting closer and closer to 0, or closer and closer to this 2 right here. Map out where that equals on this y-axis and see if it starts to approach one single number here that you could maybe approximate as the slope of the tangent line on that f of x. You can draw the f of x function onto this graph if that helps. Alright, so I will leave here, I will erase it so you guys have a nice clean slate to work on. You can pause the video, you can whatever you want to do. Go over those questions, see if you get them right, see if they start to approximate one number. They should start to sort of get closer and closer to one number on either side, and that way you will know that you did them right. And if you feel as though you've gotten them right, you can send us an email at this email address right here, buddinggenius@buddinggeniuscm.com, and say, hey, I did the quiz in the video and I think I got them all right, so can I have my coupon? And you get a 20% off discount on any summer camps. So feel free to do that, answer the questions, and then send in an email to us and say, hey, I got these answers right, or I think I got them right. And we will send you a 20% off discount code to apply to any summer camps. And I hope that you guys enjoyed the lesson today. I hope it wasn't too confusing. I hope you guys followed along, and if not, or if you're a little bit confused, you can always comment on the video on YouTube, or you can wait until the next video comes out and watch that, and we will go over some examples of what exactly that expression means and that limit means and how we can calculate it. Alright, you guys, I hope you guys have a good day, and I hope you enjoyed learning along with me. I enjoyed teaching it, so see you guys later. Bye!